Our speaker of the day is Dr. Sasmita Day. Dr. Sasmita, hope you're with us. Welcome to the session. Okay. So there is
Hello,
a brief
am I
introduction
audible?
to Sasmita. Yes, ma'am. Thank you so much. So there's a brief introduction about Dr. Sasmita. Dr. Sasmita will be focusing on bonding analysis across the boundaries. Dr. Sasmita is an assistant professor at chemistry department in Cochin University of Science and Technology. Dr. Sasmita had obtained PhD in 2010 from University of Hyderabad under the guidance of Professor A.D. Jamis. She also worked with Professor Gernot Frank at the Department of Chemistry at and Professor Institute for Fundamental Chemistry at Kyoto University, Japan, and Professor Martin Zacharias at Department of Physics at Technical University, Munich, Germany. So our research areas are the understanding of chemical bonding and reactive of complex molecules by molecular modeling and simulation in interdisciplinary areas. Dr. Sasmita, you have 20 minutes of time now. Kindly share your full screen. Over to you, Dr. Sasmita. Please go ahead.
Anyway, thank you for inviting me, and so I would like to share basically my experience with ADF. So that's my agenda of today's talk. I have been using ADF software maybe almost kind of I started using it when I was started on PhD. Unfortunately, I was in institutes like in India, like University of Hyderabad and IISc Bangalore. They had ADF software at the time. So during those days, it was not that common in India to have this software. So I got a lot of freedom and resources to try it out. But after that, I mainly started using this for the bonding analysis when I was working with Professor Gernot Franking in Germany. And from there onwards, we are kind of using this almost for last 10 years. Being a chemist, what type of work I prefer to do is my work is greatly inspired by the famous scientist, of course, the Linus Pauling. So he, in one of the places where he always mentions that what chemistry can give to other domains of science. It is the understanding of the structure and the chemical bond between the atoms, which actually guides the structure and then the reactivity and the property. So, being a chemist, we can give different angles from the bonding analysis to different domains, and we can ask questions that others may not be able to think or formulate. So starting from there, we will see. My main idea would be the structure of the talk would be like this. Can we go to the next slide? Okay. So here, among this ADF, all the modules, basically I use ADF, and today I will be focusing on a special technique which is implemented in ADF, which is energy decomposition analysis. And what are the areas? There are many areas where I have used this energy decomposition analysis. I have used for understanding bonded interactions as well as non-bonded interactions. And I will be focusing some 5 examples. And where we used this energy decomposition analysis techniques and what additional informations we could achieve, we could get using this technique, which I guess is a unique feature of ADF, and we do not have these features in other traditional bonding tools. So that will be the highlight of this talk, and I will be talking about tetralones, about inorganic electron-rich aromatics. I'll be talking how we quantify hyperconjugation effect using this tool, and some metal protein interactions, and also intermolecular interaction crystal lattice. So as you can see that there are different areas where we actually apply this energy decomposition analysis. Yeah, so this is the basic scheme of the energy decomposition analysis. So let's see, look into a molecule AB. Okay, and we can think that is formed by the two ground state fragment. One is A0 and one is B0. As you can see here, it is written with the arrow. And then this schemes provides a way to find out the instantaneous bonding energy between the two fragments A and B. So what they do and what are the steps involved is that they will start from the ground state fragments, which is A0 and B0, and consider their wave function as a psi0 and psi0 A and psi0 B with their energies as E0A and E0B. Then these two fragments will be changed according to the geometry and electron. Yeah, so as I was trying to tell that, so we have this so we have these two ground state fragments, and we need to kind of theoretically prepare them in the same geometry and electronic state as it is present in the molecule AB. So that's very important, and the energy required to do so is called preparation energy, because they will have much higher energies. That means EA and EB is kind of higher compared to E0A and E0B, and the psi A and psi B represents the electronic state that is present in the molecule. And when these two fragments A and B are prepared, then one calculate the instantaneous bonding energy between the two fragment AB, which is given by delta E interaction, that is E of AB minus E of A minus E of B. So this is what it does. But on the top of that, this delta E interaction, this energy is also divided into chemically meaningful terms such as delta E electrostatic, delta E Pauli, and delta E orbital interaction. So these terms gives idea about which factor is controlling this bond between the two fragment A and B. So this is one of the unique features which it possesses, and then one can do some more things on this. The second important factor which energy decomposition analysis scheme gives is what is called a deformation density. Deformation means the difference basically. So this deformation density is a representation which tells the charge transfer happens due to this bond formation between the fragment A and B. And that tells us, yes, and that kind of let us know what interaction is most important. Can I have the next slide? Yes, it's just yeah, stop. So here we'll take an example and probably we'll understand it better. One is left side, there is an hydrogen atom which we have, and that density can be represented as rho h, which is basically square of the wave function 1s, because that's the ground state. And we have two such atoms, and as we can see, one of them having a spin up and another of them is spin down. So when they are very far away, they are in the respective ground state. Now, when they come close and form the molecule H2, then what happens? They will form a bond between these two hydrogen atoms, and the density, now the total density will become rho of H2. And in this molecule H2, the density of this two H fragments is different compared to as they were in the ground state. And that's why the deformation density that we get, delta rho, is the difference between the rho H2, which is the density for the molecule, minus the total density of the individual fragments when they are not bonded. And as you can see in this figure, I do not know, it is probably not clear, and there is a blue ball at the center and two red lobes at two sides. So it says that that the red is charge depletion. That means from the red, the charge has flown to the center of the two fragment, that is in between the two hydrogen atom. That indicates that bond is formed. And here it also says that since the bond is formed by the flow of charge or density from both side of the bond, the two atoms into the center, this is kind of an electron sharing bond which is formed by one electron shared from one hydrogen fragment and another from another hydrogen atom. So this is what the energy decomposition analysis does. And after this, we'll go through some examples. And I actually, because of this delay, I may not actually go through all the 5 examples, I think. Can we have the next slide? Yes, so this is the first examples which I would like to discuss. In this, let us first understand that the importance of the work or importance of the system. This system is called tetralones. Now, what is this tetralones? As you can see in the figure on the left, it is there one E is written with the 2 pair of dots, and then there are 2 arrow and 2 L with a pair of dots. This E is elements carbon to lead, and the L is a donor ligand. It's a basically 2 electron donor ligand. So it indicates that in this type of system, the L ligand donates a pair of electron to the central atom E. Now, all of you will be realizing that the group 14 elements, the carbon to lead, they have 4 valence electrons. And if this bonding situation occurs, then after forming 2 bonds with 2 ligands, still the central atom possesses 4 valence electrons. Therefore, this central atom is a 0 valent compound and it contains 1 sigma lone pair and a pi lone pair. So since it has now 2 lone pairs, it can show reactivity which is a bit different. Like how both the lone pairs can be donated to Lewis acids. So it can act as a double Lewis base. So that way one can identify experimentally whether a molecule has 2 pairs of lone pair or it may be having a 1 pair of lone pair. Now this molecule or this type of molecules are not that new. It is first experimentally synthesized in 1961 by Ramirez and co-workers, so long before, and that molecule is carbodiphosphorane, which is CpPH3 whole 2. But however, at that time, this particular bonding nature was not recognized. Rather, it was shown that this molecule is bent at the central carbon atom. It's not really linear. But later on in 2006, Professor Franking and co-workers, they studied the bonding situation of this particular molecule using this EDA technique which I just described. So there they use this technique to understand the bonding nature between the central carbon and the ligand. And that way they realized that this actually is a situation which is a bit unusual, and it contains, the central carbon contains 2 lone pairs. Can you just put the arrow? There is something more to come in the slide. Can you just give next? Yes, and he has coined the name carbone. This name carbone indicates that that's a carbon atom but having 2 lone pairs. This is a little bit different than the usual carbenes, which is known that they also have this Cl2 structure, but there the carbenes has only 1 available lone pairs. And then he also tried to see whether this carbons, that means a carbon atom having two pairs, two lone pairs, they can be stabilized by carbon donor ligands or not. Next slide. So theoretically, he has shown that it is stable. A CnH2 molecule is stable in 2006. Thereafter, in 2008, Bertrand and co-workers, they have prepared such a molecule. Then the quest for having heavier analogs, that is the tetralones, has become very popular. And in 2013, Professor Roeske and co-workers isolated the first silyalone. In the silyalone, they have this cyclic alkyl aminocarbene, which is a different type of carbines, and it is having a strong pi acceptor nature compared to the NHCs. And the research continues, and later in 2016 we see the first heteroleptic silylones. That means one of the ligand is NHC and one of the ligand is the CAS. Now what is happened? It is observed experimentally that the reactivity of these molecules, they vary when the ligand L is varied. That means for NHC and for CAC, and if it is having two different combinations of ligands, that reactivity actually is different. So at that point, we thought of asking this question of understanding this reactivity of having two different ligands at this center E, and trying to understand how the tetralone character changes when I have one ligand as NHC and one ligand as CAC. Can I have the next slide? So this is the one of the robust EDA-NOCV analysis. Here you can see there are 7 schemes given, 1, 2, 3, 4, 5, 6, 7, which is shown, and all the scheme there are a lot of orbitals around. So let me just take some time to explain what they are. Let us look at the scheme 1. You can see that there are 2 ligands are drawn. One is the NHC ligand, which has a CC double bond, and one is a CAC ligand with a 5-member ring and 1 nitrogen. And then that can have an interaction with the p orbital on the central atom. So that is indicated by an arrow. Whenever there is an arrowhead, that indicates that is considered as a donor acceptor interaction. Okay, so similarly we can now understand that there can be 2 different combination of this orbital on 2 ligands. One is the sigma plus plus and one is the sigma minus plus minus. One is a symmetric combination and one is the antisymmetric combination. And the antisymmetric combination can interact with the px orbital on the carbon on the central atom, whereas the symmetric combination can interact with the pz on the central atom. Now in addition to that, there is also on the carbene there are Cn pi star. Now that can accept electron from the py orbital on the central atom. That means the perpendicular orbital. Now in all these schemes there are some places there is a double-headed arrow. So in the double-headed arrow, let's say for example scheme number 4, there are one single-headed arrow and there are 2 double-headed arrow. In the double-headed arrow, you can see that the p orbital contains 1 electron and the orbital combination on the ligand side contain 1 electron. So this double-headed arrow indicates an electron sharing bond. Therefore, using this EDA scheme, we can calculate all possible bonding combinations that can be present for this CLE bond. So that's what we have done. And can you just enter next few more times? Yeah, fine. So here, and that gives us an idea that for the carbon system and for the heavier analogs, the bonding interactions is different. And then we kind of correlated with the fact that this bonding interactions can have a great influence on the differential reactivity this molecule shows, this carbon systems and the heavier analogs. Can you go to the next slide? So this is what we, yeah, few more enter. Yes, one more. Stop. So here we are having the description of this delta rho, or this deformation density. Like we gave the example of H2. If you remember, the red is the depletion and the blue is the accumulation. So we can see that in the first case, the central atom is blue, mainly blue. That means the central atom is empty. So it is receiving the electron. But for the second case, we can see that the blue is in between the central atom and L. So that means that indicates a electron sharing interaction. And for the pi systems also, we can see that it is actually the perpendicular p orbital which is having blue and which is having red, and so that the bond between the central atom and the ligand is blue. However, in this carbon system, in addition to these three interactions, there is also a carbon p orbital which is having 2 electron, and that can back donate to the other ligand, which is the NHC. Therefore, we have here 2 sigma interactions. So we have 2 pi interactions. Can we have the next slide? Yeah, this we move on. So in this I am not really explaining. We just I am just to tell that what we understand from this slide. Yeah, no, just go to the next slide. Yeah, yes, go back. So the basic difference, so this is the exact procedure, and the basic difference that we see that the carbon system, both the lone pairs are kind of utilized. So they are so the lone pair is more utilized in that, so they can be best described or closely as more of a carbene system, and which is as we can see as a resonance hybrid, whereas the heavier analogs, they have more lone pair characteristics on them. So they can be more described as a tetralone. And this probably happens because of this pi acceptance difference property between the CAAC and this NHC. And also because there is a weak sigma donation when we go down the group. So this is what detailed bonding analysis in one of the case we did, and which is a highlight of ADF, because this type of understanding is very unique for the ADF software. So can we have the next slide? Yeah, yes, go back. Okay, so here quickly I will tell, this is about the inorganic aromatics. So first we are talking about some simple sigma bond and pi bond. Here we are talking about aromatic conjugation. So we have taken a system which is inorganic aromatics and which is electron rich. And because those systems are not that much well studied as compared to the systems which are isoelectronic to aromatic organic aromatics like borazine. So here we have sulfur nitrogen compounds, and as you can see, which is given, the some of them are stable and some of them are not stable. So in a quest to understand that, we have undertaken the bonding analysis, and along with the traditional bonding analysis, we have also performed some extra analysis with the EDA. So that's what will be my main highlight. Can we have the next slide? Yes, few more. Yes, fine. Go back. Okay. So here, one thing we need to understand is that this systems, this S3N3 minus system, they have 10 pi electrons, and everybody knows that it looks like benzene. It's a hexagonal system. So benzene has 6 pi electrons. So this has 4 additional pi electrons. And what we see is that these 4 additional pi electrons are basically required for the system to be stabilized. So what we understand is that if we look into the two molecular orbitals, which is pi 2 and pi 3, since there is a huge electronegativity difference between the sulfur and the nitrogen, these are mainly concentrated on the nitrogen. Whereas in case of benzene, the pi 2 and pi 3, they will be equally distributed. So 6 electron is enough to have an uniform electron distributions for hydrocarbons, whereas these systems, they actually require additional number of electrons to have to get this uniform pi electron distribution, which is a characteristic of the aromaticity. Next slide. So in this we this is enough. So in this we have fragmented. As you can see, there is a picture is drawn. So there are many single electron, double electron. So we have fragmented this molecule into 3 different fragments, and we used different possibilities to understand which is actually the best possible bonding interactions. And here what we mainly understand is when we understand about the total energy which is required for this bonding, we can also divide it into different components. So here you can see there are components which is on the left side of this table, like electrostatic, orbital, then delta E sigma, delta E pi, and so on and so forth. So the important things are highlighted into the red and the green color, where we can see the molecule which is S3N3 minus, it shows a high amount of electrostatic interactions, and it also has a high amount of delta E pi interactions. So whenever we are adding additional pi electrons, the delta E pi increases. However, the major factor which we understand is that the other fragment, which is highly charged, has very less electrostatic stabilization for the stability of this molecule. So these are the analysis which we can do using this EDA techniques. Can I have the next slide? Yeah, just go on. Yeah, stop. Go back. So here, so far we are talking about interactions between 2 atoms. They are bonded. Here, as you can see, this is an adamantilidine, and you can see on the left side, it is shown that the bridge, the adamantiline bridge, which is a carbon, is bent, which is like Norbornene type of system. However, the Norbornene system, the empty orbital on the carbon center is compensated by the donation of the double bond pi electron. So it's basically work as a nucleophilic, whereas in adamantilidine it is an amphiphilic. So it's again an interesting topic for organic chemistry to understand these reactions. And the stability of the systems is mainly governed by 2 type of interactions, which is shown here. As you can see, both the interactions are non-bonded interactions. So one of the interaction, which is A, that indicates the CC, the nearby CC bonds, they donate electron density to the empty p orbital at the bridgehead. And the B scheme shows that the lone pair at the bridgehead, that donates or transfer electron density to the nearby CC sigma star. Next slide. Yeah, go on. Okay, stop. So go back. So once again, I will be mainly highlighting what EDA can give, which other bonding analysis or techniques cannot give. So in this case, what we can get from this understanding is that there is again the table. Probably you will be familiar with the table by this time. So there will be a lot of energy data that we get. The most important data is that here we have compared between 2 structures, 2 and 2 prime. 2 is the bent structure, 2 prime is the structure where the bridge is not bent, and we compared between them so that we can understand what is the reason for bending. That was the question that we asked. And there are 2 energy terms which is given as delta E H1 and delta E H2. The H1 and H2 we have introduced in the previous slide. And in this we can see that the difference between the 2 and 2 prime is mainly coming from the H1 type of interaction. So if we try to understand in between these two hyperconjugative interactions, which is a major, we can say that the analysis shows the H1 type of interaction is the major reason for it to bend. But still, since the H1, you see that it is like donating the electron density to the empty pi orbital, but since it is not having a very high large energy term, the p orbital still is electron deficient, and as a result it works as an ambiphilic. That means it can donate a lone pair of electron, it can accept a lone pair of electron. So one single atom acts as both Lewis acid and Lewis base at the same time. Next slide. Now we're going into a different domain where we also use. So here is another problem where we kind of try to understand about a chronic beryllium disease. So this is this disease occurs very simple language. This disease occurs because of the interactions of beryllium ion with the some protein in our body. And what happened is that at the end, as you can see that our lungs, we have this vessels and all these things which is required for our normal respiration. There we get blocked. So that is called the lung disease and breathing trouble, and that leads to several health difficulty. Can we go to the next slide? Just slowly do. So here you see there is an animation which indicates that how this disease form, and in that animation, since you realize that there will be some metal which is a ball which comes in, and then there is one more protein comes. So after the metal comes in, there will be allosteric interactions at the surface of this protein which enables binding of the second protein. So this is what the mechanism is, and in this the interesting question was why beryllium is the only one which is acting as a toxic metal. Can you click next? Whereas the heavier congeners of beryllium, such as magnesium and calcium, they actually are not toxic. And at the same time, the essential metal ions like sodiums, they are also not toxic. So they cannot bring the similar structural change that a beryllium can bring to this protein. Now we wanted to know a little bit more detail about it. And then what we did that first we have run an molecular dynamic simulations on this whole systems, and we identified the binding sites for sodium, magnesium, calcium and beryllium. And once we have the binding site, on that binding sites we perform this energy decomposition analysis using our density functional theory. And there we realize that there is a correlations with the electropositivity of the metal and the binding energy. And it is also found out that the beryllium, which is showing high binding energy, that comes from mainly from the covalent contribution of the beryllium, whereas for others it is not so. So that part of the analysis we used ADF and its energy decomposition analysis to come to that idea. Can we have the next slide? So this is the last example. Now go back. This is the last example that we have, and here as the title suggests, it is about the intermolecular interaction. So left there is a molecule is which is a porphyrin, that is a fluorinated porphyrin. It formed different crystal structures. And the question was in front of us again, that what are the type of interactions they basically involved when it forms the crystal packing, because the understanding of the crystal packing is very important for the crystal engineering. So here we have 4 molecules, 1, 2, 3, 4, and we have performed the EDA on this crystal lattice by taking a dimer as a mimic, and then we plotted all the components of the energy. And from there we realized that this is stabilized because of the presence of the fluorine atom, and it is the fluorine atom which is giving a fluorine H interaction, fluorine carbon and fluorine aromatic interactions. And out of the all component, it is the dispersive interactions and certain structures, they are important, and they are acting as a guiding or governing factor for the particular crystal motif that we have. So this way, what I try to show as a 5 example in 5 different situation, we use this bonding analysis technique, which is unique to ADF, to arrive at conclusions which would not be possible probably with any other tool all the time. Last slide. Yeah, so as an acknowledgement, I would acknowledge the funding, because without the funding we cannot buy ADF. So funding is very important because we have to buy ADF license every year. And we also need computational facility, so which is provided by our university and other funding agencies. And on top of that, we will be like to thank the collaborators here. And I just would mention about the last intermolecular interaction that we said. So that work was done with Dr. Arun Kumar A, and unfortunately he is not there amongst us anymore. But still, we remember, and I just want to pay my respect to him, because it is kind of work that we do, and we really miss him in this journey. So that's my talk.
Thank you so much, ma'am, for your informative session. And we are extremely sorry. Sorry for an inconvenience caused and keeping you on hold. So let's quickly get into a Q&A session. I request if anyone having a question, you can unmute yourself. Any one question can be taken now. Rest of the questions we will take via Discord due to restrictions of time. So anyone having a question, you can unmute yourself and ask to the Dr. Susmita.
Yeah, I have set a question in the chat box. Can you read it, or shall I read it out?
Ma'am, do you have access to chat?
Yes, I have seen that. I have seen that.
Thank you.
I have seen that thing, and I have seen that paper. And this is not only one. There are several papers like that which says many things about it. But in this particular paper, if we read carefully, here what they try to say is that the EDA cannot be used to find out the absolute energy situation. So it can be used to compare between two molecules which have a similar bonding situations. So because it is not, so that's what they talk about, path functions and all these things. So if you take one and you cannot have idea about whether that is the thing that you are getting the energy, they are in absolute terms. So that's what their main criticism about this EDA methods of analysis in this particular paper, if you read it clearly, this PCCP.
Yes.
So what we did is also the same thing, because every time you see, we try to understand which component may be working better. So we have several similar systems, and we compare between them to find that idea.
Okay, thank you very much. Thank you.
Sure. So rest of the questions will be taken.
Yeah, there is one more
Yes,
question. How was the molecular dynamic simulation done? I mean, that is not done by ADF. That only I will say here. Because I just can we calculate NOC from the EDA analysis? I think it's there in the ADF. And it is there in the ADF. Yes, but we don't need EDA as far as my understanding about it, but it is possible by ADF, I guess. I'm not sure. I have never done it, so I will not be the best person to answer.
Sure. So rest of the questions will be taken via Discord. Sorry for an inconvenience. Dr. Susmita, thank you very much.
Yes, thank you.
So let us quickly get into the second session. So our second speaker of the day is Dr. Vijay Kumar Solomon. Dr. Vijay, hope you're with us.
Yeah, yeah, fine.
Yes, thank you so much for being part of this session. So there's a quick introduction about Dr. Vijay. So you'll be focusing on designing organic ligands for effective lanthanide, actinide separation in nuclear waste management, a DFK perspective. So he is an assistant professor at Madras Christian College. Vijay Solomon obtained his PhD in 2012 under the guidance of Professor P. Venuvalingam. His current research areas are modeling nanomaterials and excited state properties of molecules, biomass conservation of and nuclear waste treatment, a modeling of metal, organic and biocatalyst reaction, chemical bonding, chemical reactivity and weak interactions, heterogeneous catalysis and molecules for solar cell applications. Uh, Dr. Vijay, you have 20 minutes of time.
Yeah.
So you can please share your full screen and you can go ahead, sir.
Yeah. Yes. Okay. I think is my screen visible to you?
Yes, sir. You can share your full screen. Yes.
Yeah. Fine. Okay. So am I audible? Is that fine?
Yes, sir. You're audible.
Yeah. Time is running out, and quickly we'll get into this topic. And once again, good evening. And I would like to talk about how ADF can be used to understand the chemical bonding. Especially, we work on coordination chemistry, and we would like to understand the metal ligand bonding. So, in that aspect, we venture into this particular topic of nuclear waste management with the project from DST SCRB. And we have done quite a lot of work here, and I would like to present three of our works here. Um, let me start. Okay. Before getting into the real, computational part, we should know that why do we want to do. If you look at that, the global emission due to CO2 is mostly from the fossil fuels and its usage, and people are started thinking about the alternate energy resources, and here comes a green and clean energy. So far, people are referred to the nuclear energy. But if you look at the process, there are plenty of processes associated with the treatment of the content. And if you look at that, we need to start with mining. Then we need to enrich the fuel fabrication. It will taken into the nuclear reactor and the power generation. Followed by we need to store them, and we have a spent nuclear fuel which causes a lot of problem, and then we need to safely dispose the waste. But if you look at that, the spent nuclear fuel is the major threat, and I would suggest that the spent nuclear fuel will have a lot of components in that, starting from plutonium, uranium, and minor actinides. And these actinides are present in very small quantity, and it is like 0.1 out of the entire stuff, but still it plays a major role in causing the radio toxicity. So minor actinides mainly neptunium, beryllium, and Cu. I think somebody has muted that, and can you ask them to mute that? Yeah. If you look at that, yes, we do not have much problem in other aspects, but when it comes to handling the spent nuclear fuel, so we may not have a big problem here, here. Up to power generation, we are very happy. But when it comes to the spent nuclear fuel and handling this, we have huge issues. Why? Because this particular spent nuclear fuel contains multiple radioactive elements, mainly lanthanides and actinides, and which have different oxidation states. Something is like +3, +4. There are plenty of oxidation states are possible. But usually, what we are doing here, the spent nuclear fuel, we have a major component of uranium and plutonium, which can be separated from the container using the method called Purex. And the other lanthanides and minor actinides, and especially the minor actinides, which causes a huge problem and a potential threat to human and the biosphere. So this is highly essential to remove the actinides from the lanthanides. If you look at that, why do we need to do that? We have seen that it is a huge threat, but there are a few ways we can do that. The minor actinides can be converted into a short-lived or stable nucleotides so that we can separate it. And on the other hand, lanthanide absorb neutrons effectively in the high-level liquid waste. So if you look at that, if we remove the actinides from that, and that will lead the process in a smoother way. So we need to remove that. There are plenty of ways available, but the most efficient way we need to look into that. For example, look at this. Lanthanides and actinides, as a chemist, we have a huge challenge in distinguish these two. For example, these things, these two, lanthanides and actinides will have a similar ionic radii +3 oxidation state by and large, and electrostatic forces and steric factors. And it is very difficult to distinguish these things because when we say that identical twins, very difficult to distinguish them. But courtesy to the HSAB principle, where we know that even both are considered as a hard Lewis acid, but the actinides are slightly softer than the lanthanide, and we capitalize that, and we would like to come up with the complexation process with different soft donor atoms, mostly nitrogen, and sometimes nitrogen and oxygen, sometimes people are saying that sulfur and so on. So in our work, we tried our level best to understand the complexation behavior of certain organic ligands with the actinides and the lanthanides, how good these ligands are in trapping the actinides, leaving the lanthanides. Okay, that is our idea. With that only, we tried our level best using the computation techniques. So broadly, I can classify that identifying the molecular origin of selectivity towards actinides over lanthanides. Most of the reports said the organic ligands with the softer donor ligands are more selective in picking up the actinides. Why do they so? Understanding the nature of metal ligand bonding. Obviously, like when we look at the bonds, we want to understand the bonding nature. And can we tune the selectivity through proper modeling? That we tried. And if you look at the coordination chemistry, we know that different coordination numbers available. Can we play with that? And our idea is to identify the potential ligands based on the electronic, steric, and energetic factors that govern the selectivity. The possible reasons by which one can think about the selectivity of these ligands. All these objectives are in our mind, and based on that, we started our analysis. And we use ADF software for optimization and other purposes. And we did some population analysis. And in order to quantify the strength of the bond, metal ligand bond, we have calculated the bond orders of metal ligand bonds are mostly N or MO bonds, and the non-covalent interactions associated with the molecules. Then we look at the smaller interactions from QTM, quantum theory of atoms and molecules, which is implemented in ADF as an inbuilt feature. And obviously the unique feature of ADF is like energy decomposition analysis is done to understand the contribution rendered by the metal to the ligand. And we found out the thermodynamics feasibility of the complexation process. Now, the first study is about the triazinyl pyridine ligand. And what we did here, we know this is a ligand that we would like to work on, and we studied about their interactions with the ligand, the lanthanides and actinides. So here we picked few representative cases of the lanthanides and actinides. We picked cerium, uranium, and europium, americium, and CM, we'll see. And if you look at the experiment says that these metal atoms are always associated with the nitric acid medium, and they form a MNO3 thrice. Usually metal is in +3 oxidation state, the +3 charge, and this is interacting with the ligand to form MLNO3 thrice. So when we want to understand the complexation behavior, we need to pick this stoichiometric ratio, and we need to work on that. Yeah. So any property you want to calculate, you have to go for the optimization of the ligand that we did. So this is optimization of the ligand of CE complex ND, EU, U, AM, and CM, and the free ligand is given here. If you look at that, the free ligands, if you see that the OCH3 group is pointing, away from the cavity. Cavity in the sense the place where it can interact with the metal ion. So upon complexation, you look at that, the CH3 is, from the outward, it turned into the inward position, because it can form some interaction with NO3, weak interaction. So the flexibility of the ligand is confirmed here from ligand to the complex. And when we look at that, this is a highly delocalized molecule, and we can understand from the bond lengths, because we know that carbon-carbon single bond is 1.54 and carbon-carbon double bond is 1.32. If you analyze any molecule, if we find throughout the molecule the bond length lies between the single and double bond limits, then we can say that the delocalization is complete there. And if you look at that, the cavity size, the free ligand has a cavity size. So how can we understand the cavity size? We can look at the distance between N1 and N5, or N2 to N3. So we can pick the distance, and we call that as a cavity. And what happens after the complexation? If you look at that, AM complex has the smallest cavity, and the free ligand has the largest cavity. So AM is trapped well into the cavity of this particular ligand. Then we looked at the bond parameters like bond angle. I didn't discuss about the bond angle. We talk about only bond length. Bond length. So if you look at that, you have MN1, MN2, MN3, MN4, MN5. There are 5 nitrogens. 1, 2, 3, 4, 5. And if you look at that, the distance, like this is 4.7 and this is 3.4. So this is there. The complexation, if you look at that, these two are very closer. This is like longer than the N2 and N4. Look at that here, 2.5, 2.5. And this one is 2.6. So if you look at that, the umbricium or any laminate arachnate, when it wants to have a bonding with that, we need to understand whether it is having a bonding with this or this. I mean, the strength. Strength can be directly correlated with the bond length in most of the cases. Then we looked into the frontier molecular orbitals as SOMO and LUMO, and their energies are given in electron volts. And this will help us to understand the chemical reactivity of the molecule. Once a complex is formed, if we have a free ligands, we can look into the chemical reactivity. Most of the cases, people have used this to understand the optical activity as well. Then we did the population analysis and the charges we have calculated, and how the +3 charge of metal atom, because I said metal is in +3, how that is reduced to +1.7 or something, because it forms a bond with the nitrogen atom of the ligand. So this is reduced, so which tells that a strong donor-acceptor interaction present in this particular complex. Nitrogen atoms in the AM and U complexes have greater negative charges, which means the greater bonding is expected. N3 and N4 overlap values for U is greater than all other complexes. As I mentioned, that N3 and N4 have shorter bond length. So this is well reflected. We again calculated bond order for these bonds, and bond order analysis tells that the bond length and bond orders are in line with the expected result. Then we did QTM analysis. This analysis is available in Gaussian and other softwares, but here it is an inbuilt feature, and you can get the molecular graphs that are displayed here. If you look at that, the bond path are connected between the two atoms, indicates that there is a interaction between any two atoms. We can use this particular QTM analysis to understand the chemical bond. It's a covalent bond, coordinate bond, non-covalent interaction, anything is fine, as long as a two atom, let's say A and B, if you find a bond critical point between two atoms, that tells that there is an interaction between the two interacting atoms. And if you analyze this, because we can analyze the topological properties, I mainly concentrate on the electron density. The electron density is given by rho, and if we looked into the rho values, we can say that the strength of the interaction. So one thing you need to keep in mind, that if you find a point between the two interacting atoms, that tells that there is an interaction. And don't worry about that whether it's a covalent, non-covalent. There is a interaction between the two atoms, and if you click that and if you find the properties, that will give strength of such interaction that we have calculated. Again, this is in line with the bond length that we have calculated. Now, the famous energy decomposition analysis we did, considering the MnO3 as one MnO3 thrice as one fragment, and then the ligand as another fragment. And if you look at the total binding energy is given here, and you can see that uranium is having a higher total binding energy. Then you have americium. In all the cases, the actinides are better. Actinides are having better binding energy towards this ligand compared to the lanthanides. This is once again in line with the experiments. And if you look at that, the orbital interaction energies are key forces here, because these are all driven by the covalent bonds, coordination bonds, mainly the metal and nitrogen interactions. So we conclude that the metal nitrogen bond lengths are shorter in actinides than lanthanides, and the energy decomposition analysis says that the orbital interactions are the key features in dictating the terms to the binding energy. Okay, this is the first case study, and we published this in Chemistry Select. Then we looked into that. Okay, why don't we go for a mixed ligand, nitrogen and oxygen? So we picked this particular case, TM-Fen-Da ligand. And here what we did, we looked at the flexibility of this particular group. Because when we want to find, when the metal atom is interacting here, and the particular groups that are there as a wings, and that can undergo rotation. So we did a scan. A scan is another option where the diagonal angles are varied, and the energy relative energy is plotted here, and we find that which is the optimum the bond diagonal angle this particular molecule can have. Then we moved with the complexation process, like starting with the optimization. Okay, and again, this is frontier molecular orbitals to get to know about the reactivity of such complexes. And then we did QTM analysis. The interesting case is all these molecules, like the previous work and then work, we have NO3 thrice. So if you look at that, M is having already a 6 coordination with this O, this nitrogen O. If you look at that NO3, so already this is like a big, big molecule, big structure. Then it will form a coordination bond with this, the ligand. So it is interesting to look at that. What is the role of this particular NO3 thrice? It is not only giving a bond to metal, it also involves in other interactions with the wings. So you can find a lot of small, the bond paths, which tells that apart from coordination bonds, we have other stabilizing interactions which governs the stability of this particular type of molecules. An energy decomposition analysis is done, and again, this is like a place where you look at that. Always the orbital interactions are holding the key. If you look at that, few cases you have electrostatic interaction, but if you look at that, orbital interactions are mostly higher than the electrostatic interactions, except in only one case. But most of the cases, this is the trend that we got. So when you think about nuclear waste management and the metal ligand bond, and the orbital interactions are very, very important, and that play a vital role. So here also, like very similar conclusions, that the coordination bonds are very important, and some other small contributions are obtained from the NO3 with the wings of that. This we published in Journal of Molecular Lipids this year. Then Now, two things are over. The final one is like, we thought that, okay, let us not tune the metal atom. Let us take a pair, which is like americium and europium. One is actinide, one is lanthanide. And how one can tune a particular ligand using our chemical intuition. That's what our idea. And we thought that let us take a 6-membered ring and let us take a 5-membered ring and we attach to this ligand and let us see. These are the 6 ligands that we identified there. This is a 6-membered ring and this is a 5-membered ring. And with that, we have added a phenol group here. This is like a single substitution, and here we have a double substitution. And we try to understand, okay, what role this particular substitution plays in the selectivity and the binding affinity of these design ligands. And optimization is done on that. Again, we looked into the various bonding parameters here. Then we prepare the complexes, as I mentioned, that MnO3 thrice. We maintain constant throughout our study, and we looked into the frontier molecular orbitals. Then we did in vivo analysis to understand the charges. We have taken in vivo charges, and what we did, we looked at the ligand and we looked at the charge of that particular atom in the AM complex and EU complex. If you look at that, the free ligand and AM complex and EU complex, and all these small ligands are following a very similar trend, and you can look at that from different graphs. Then again, we did the QTM analysis, and here we found that additional interactions with NO. Sometimes what happens, like the two electronegative atoms are also showing interaction in QTM, but that is contributing to a very lesser amount because very small rho values are obtained. On the other hand, we picked up the rho values, Mn1 and Mn4 are greater than the other two. So if you look at that, the ligands which are closer, this is having higher rho values and stronger bonds compared to the one with N2 and N3. Okay, and the values are given here. The rho values are plotted here. And when we think about complexation, we cannot leave this fellow. This is called thermodynamic parameters. We know that a spontaneous reaction will have a negative del G value. And of course, we got del G values. We can calculate here. And we can find out del G value to calculate the separation factor. And the separation factor sometime can be compared with the experiment. We did all the calculations in gas phase. Therefore, we didn't compare with the experimental values. But some of the papers, we can see that they compared with the experimental values. And the calculated values are in line with the expected results, that these molecules are good in picking the actinides compared to the lanthanides. And the 6-membered ring with 2 phenolic substitutions is the best molecule compared to all other molecules in extracting the actinide selectively compared to the lanthanide. Okay, energy decomposition analysis is done, and if you look at that again, you can clearly see orbital interactions are higher than the corresponding electrostatic interactions, and in all the cases the repulsion is more or less satisfied by or countered by electrostatic. So the total interaction energy or total binding energy is purely obtained from orbital energy. For example, if you look at that, the minus 7.4 and here 7.3, 5.4, 6.1, 7.4, 7.4, 6.2, 6.9, which means that almost all the cases in this type, we observe that orbital interactions are the main key element in dictating the terms to the total binding energy obtained. So this is our results. And in summary, we can say that when we tune the ligands, not all the nitrogen or oxygen atoms involved in the bonding leads to the total binding energy, but few bonds or 2 or 3 bonds which are closer proximity to the metal atom and shows a strong bonding nature through QTM and shorter bond length and better bonding bond order, that actually plays a role. And almost all the complexes show negative del G value, and the feasibility of complexation process is ensured here. So our takeaways from here is, if we want to understand the chemical bonding, I would say that you can start with optimization, then you can look at the bond order, then you can look at the QTM, and further we can do EDA, and you compare these three, all these will fall in line, and you will come up with the beautiful information and insight about a particular chemical bonding. So I would like to conclude with that, and this particular paper we published in Inorganic Chemistry Frontiers recently. Okay, I acknowledge Madras Christian College for having me as assistant professor in Department of Chemistry, and I thank DST SCRB for the Early Career Research Award as a major research project to carry out this work, and through that only we have got ADF, and we are working on that. So at this juncture, I would like to thank our computational chemistry laboratory, for carrying out all these works, and most of the work are carried out by Mr. Cherian, who is my PhD student, and the second work is carried out by Mr. Lipin, now who is doing PhD in Ireland now after a master's at MCC. And this is our laboratory in Madras Christian College. And this is like, a present group member. We have Cherian, we have Abihail and Midun, and this me, and this is Lipin. Okay, so I thank all of them at this juncture for a very productive year in MCC. Thank you for your patience. Thank you.
Thank you, Dr. Vijay, for your insightful session. So let's get into Q&A session quickly. So anyone having a question for the Dr. Vijay, you can ask. You can unmute yourself, please. So we will take any one question, and rest of the questions will be answered via Discord. You can put your questions in the Discord.
Yeah. So I got one question, like, you did a coordination scan for the ligand. The metal you selected, if you did, how you do it with the area? No, the scan option, I didn't do it with metal. I did the scan option with the change of diagonal angle, and I predicted the energy. That's number one. Number two, like, why 6-membered ring is far more stable with the LNN 6-membered rings, and it is not only 6-membered ring and with the phenolic groups. And the point here is, when you substitute 6-membered ring, that actually alter the charges on the nitrogen atom, which are interacting. So if you take a core moiety, and only if you substitute anything in the peripheral region, no problem. But before choosing a ligand or before going for the complexation, let us just look at the charges on the nitrogen atom, because they are going to interact with the metal directly. So that is playing a major role, I would say. So in that way, we can say that.
So thank you, Dr. Vijay. Thank you so much.
Yeah, thank you.
So let's we will get into the session, the third session. So our third speaker of the day is Dr. Thomas Soini. Dr. Thomas Soini, hope you're with us. Welcome to the session.
I am. Thank you very much.
Yes. So there's a brief introduction about Dr. Thomas. He'll be focusing on transit state search. He's a support scientist at SCM. Dr. Thomas obtained his PhD in group of Professor Roch at TU Monchin. He was studying transition metal clusters with DFT methods with reduced self-interaction, and working as main developer of program Paragos before joining SCM in 2015. Dr. Thomas has been working on improving electronic structure, engine, and geometry optimizer. He helps our users with setting up scripts and works on advanced case studies. You can also find Thomas at conference and teaching workshops across the globe. Dr. Thomas, you have 1 hour of time. So kindly share your full screen.
Yes.
So over to you, Dr. Thomas. Please go ahead.
Calculating the transition state, one needs not only to have a geometry which is in the vicinity of the actual transition state, but also usually it's handy to give the program some idea of what kind of direction should we search the transition state in, and that is the reaction coordinate, the reaction mode. We can set that up here by marking these 2 atoms, so the carbon and the chlorine. and we click here on plus for direction coordinates, and you will see in very tiny fonts written here that this is the distance between these two involved atoms, plus or times a weighing factor. We repeat the same for the other bond between the fluorine atom and the carbon atom, and click on plus again here, and then you will see another of these distances popping up. So what we want to achieve here is that one of the bonds basically is shrinking while the other one is growing. To achieve that, we can simply type in here -1, or we click on this one, on this symbol here, and it will automatically add the -1 in this. So yeah, having set up that, let me just quickly check that I did not forget anything. Indeed, we also would like to calculate all the frequencies all along, which serves in a moment to indeed identify our transition state. So with that, I can save my calculation, and I can just run it by pressing Control and R. And so this is a very fast engine. This happens rather quickly. So with that, it is already done. I can import the new results, or more precisely, the localized structure of for our transition state. So next, it's always handy to look on how did this transition state search actually go. For this, we can open here by pressing on the SCM button and clicking on Movie, which opens the AMS Movie subprogram here. Let me enlarge that quickly. And so here you see the progression of this transition state search. Note the graphs here, which display the energy as well as the gradients. And as this is not a minimization, but rather a search for a stationary point, you can see the energy will go up rather often. However, the main point is that the gradients are converging towards 0, which is the case here, and you will see that this is indeed the final result of this iteration. To confirm that, we can then open the AMS spectra program, which in that case, as we requested to calculate vibrational frequencies, that will show them and display these vibrational modes. So the most important thing here to take away from is we are looking for a transition state, which conversely means that there is one and exactly one mode having a negative frequency. Looking at that, that is pretty much what we as a chemist expect. So the carbon basically flips between these two atoms, or viewed differently, one of the atoms goes in and the other one gets kicked out, and this is our transition state.
Dr. Thomas?
Yes.
Sorry to interrupt. Can you increase the font size? We are unable to see.
I can try. So let me maybe scale my screen up. That is usually better in such situations. So is that better for you?
Can you increase a little bit the font size to? Yeah. Yes.
Yeah.
It's visible.
Mm-hmm.
Yeah.
Probably this is. So you will see here the aforementioned negative frequency, and that's actually for a simple system like that. That's all we are interested in here. So I would suggest I give you like 1 or 2 minutes to try that out briefly, and I'm suggesting, I am entertaining some questions if there are any with regard to that. Okay, shall I move on with the next exercise maybe?
Sure, Dr. Thomas. I guess there is no questions as of now.
Okay. Yeah. Indeed, because we're also given the time situation, it might be better. So the next approach is slightly more complex and also a bit more costly regarding calculation time, but on the other hand, it is able to deliver basically the full reaction path, because it uses a discrete set of different images of the system, which are propagated along the transition or the reaction path. And so each of these images, so-called beats, are connected by virtual strings. So some ghost force pushing the systems apart, making sure that they are more or less equidistant along the transition path. And so basically it means that the whole system needs to calculate a whole set of different geometries all at once. So with that, we move on and import the example molecule for that. So you will find also probably in the, no, that is not the right one, sorry for that. You should be finding the example of the zinc oxide surface model here. And we import, so there are two, one is initial and one is final. And we import the first one, the initial one, and then also the second one. So probably the main thing is they need to be distinct, of course. And so then what you will basically see is here at the bottom there are two tabs, and they can be then you can switch between them. I will call one of these initial and one of these final. And so having set that up, we move again to a faster engine for the sake of this tutorial. We use ReaxFF because indeed there is a reaction happening, and we use this ZNOH.FF force field. We can then also set in some details which are more technical nature. So I can switch here to expert ReaxFF and select the direct charge solver. That is because Reax, for being a parameterized force field, it can deliver quite a rough potential energy surface at times, and therefore we would like to smoothen that out. That is what this is for. So next we move here in the details tab. So we select task NEB, and we then select the details by clicking the arrow next to it. We can here select the endpoints of this chain of structures, so then the notched elastic band indeed, and we select initial and final for the initial and final system, and these correspond to the names I have just given these individual snapshots of the system. So with that, there are a few more instructions, I think. We enabled the frequencies, we loaded the systems. I will keep 8 images for the time being. And I saved the whole calculation, and then I just let it run. So if we set this up correctly, we can then again see here by opening Smoothie. So what we get now is basically, you can also observe this while the calculation is running, by the way. You just have to make sure that you are then showing, you will see how the system progresses, and but in the end, when everything is converged, it will show you a result like this. And what you can see here is if you move along the frames, you will see this water splitting reaction happening here. So basically this hydrogen here, it moves from one oxygen on the surface to the oxygen of the adsorbed OH group. And as you expect for transition state, here in the middle, there will be a higher energy. Eventually, we can also look into the gradients, and you will see again here at the peak where the energy is highest, the gradient should be close to 0, which is the case indeed here, which is one of the properties we expect to see for a transition state. Again, we can then move to AMS spectra, and again, looking at the frequencies. Again, here we are interested in the one and only mode who has a negative frequency. We can see this confirms it, so our action is indeed this hydrogen atom moving. So at this point, are there any further questions? So I see mostly technical questions. Hybridization. So far, yeah, that probably relates to the previous exercise. That is the question from Abigail. So yes, you can also look at orbitals along the way. The thing is, in our case, we used a very fast engine, so I'm not sure if MOPAC can actually display orbitals. It deals in terms of orbital shells, as far as I'm informed. But yeah, if you repeat the same approach with ADF, you should be able to see the orbitals for each of these.
Dr. Thomas, is it possible to view the orbitals which are in between? Because we are aware of sp3 orbital, but is there something beyond that or something that causes intermediate hybridization?
Well, it depends on the model you're using, right? So right now, all this transition state relies on some engine giving you back an energy and a gradient, which is all which is used here. However, you can, for individual systems here, you can probably pick them out. So if we open, we open movie again. So what you would do in such a case is you go towards the end, you pick the transition state, and actually that's in that case it's already selected. So with I'm not sure what MOPAC gives here exactly, to be honest, but I am sure that when you use so maybe we can see here some, if this works here. No, it does not. No, there are no data. There's no data stored here as far as I can see. So currently it's not working, but that's how you would load the orbital pictures in here. The only other thing which comes to mind is maybe we can see some orbital levels here. That would be a possibility, but you see already here, this is basically an entire shell which is only partially occupied. Yeah, there is no orbital information here, I'm afraid. This will not do anything. But with ADF, where there is actual, where the electronic structure is resolved down to the individual orbitals, you can easily get that. You can open AMS levels, and then you click on the level you're interested in, which is usually a frontier orbital, and then you can inspect whether this corresponds. Yeah, you can also inspect the composition, so how many, what's the amount of carbon P and carbon S, as well as what is contributing to the formation of this orbital.
Thank you so much.
Yep. And then Nilo asks, can we get the mechanism of water splitting using inorganic materials using this model? Yes, so the mechanism usually, so when you're at that point, you usually calculate already a part of the reaction mechanism, right? You're pretty sure that the system moves in between these two local minima or intermediates. However, that is a good question, because what I was planning next on showing, if we have a little bit of time, is indeed this automatic PS exploration. Which is a very new feature in the AMS modeling suite, and that is more akin to your question. So to get these tutorials, you can find them on the accompanying documentation on tutorials, which you can simply click by access by clicking help and then tutorials in the graphical user interface. There are a few newly added exercises here. So one of these, for example, is the 1-chloropropane, and let me just reload a fresh input screen here. So what we can do is, for example, select search for the 1-fluoropropane here. Fine, I can unfortunately not see it here. I am hearing some background noise. If
I request everyone to mute. Thank you.
Thanks a lot. Thanks a lot. Just let me load this in. Sorry. Right, that looks better. So we are basically studying this molecule and yeah, the different configurations or isomer of it, which basically constitute minima on the potential energy surface. So again, we are studying this with something fast because this actually requires a lot of different individual calculations. We have this molecule and then we can, for example, generate another isomer. Let's say one way to do is just enable the dynamic bond search and just rotate these two atoms around here. I can also click on pre-optimizing them, and then it should put them in a reasonable position. So now that we have set that up, actually we can also add our original molecule here. I copy this one and in here again, I again bring this to a different position here and pre-optimize these atoms again. So what we should have now is yeah, two isomers of this molecule. And what we're going to do now is basically we enable our PS exploration here, and that gives us access to a yeah, subset or collection of individual tools which are all aimed at yeah, studying many systems and studying indeed individual reactions connecting minimas on the potential energy surface. So with that, we enable process search here. And let me quickly explain how this works. So what we do here is basically we have different, we start out from one or more minima, and we randomly explore how the system behaves when moving along the potential energy surface. So we can get out of a local minima, eventually end up somewhere on a transition state. So again, that's a stationary point on the potential energy surface, which with one negative frequency. And from there, we can eventually move into a new minimum. There are also searches which are not so successful, which end up nowhere and which are deleted thereafter. So this systematic exploration is rendered possible by the so-called EON library developed in Iceland. And yeah, it binds together different implementations. So this so-called process search, which is essentially what I just talked about, a Monte Carlo based basin hopping implementation, which basically takes larger strides, and then an analysis localization of different adsorption sites is also implemented, currently available. So with that, I select the number of expeditions. So basically how often is such a search started, and then we can parallelize this over a number of explorers. And I need to check if that is already everything which is required here. That looks pretty much the case. And yeah, with that in mind, I can save this and run this job. So if we now set up everything, you can then see that the system will start start up this exploration, and it will. So this will take a while, of course, and it requires a certain amount of time. So what you can then see, for example, you can monitor the whole thing in AMS movie again. And what you will see then is that starting out from these two local minima, which were basically the input, it should be able to find new structure as it moves along. And so to speed this up a little bit, I think, I will then just directly move on to what you should see if this is successfully done. And so what you should then see when this is concluded, it tries to build here or to map out the entire reaction network between different minima. So if you recall, the order was slightly different here for the starting geometries, but afterwards we see here, for example, if we look at this one chloroisomer, we see that there is a, if we zoom in here, we see that there is a transition state in red here, which is rather close and very low in energy, and it actually leads to another local minima. So if we look at this and compare these two, or respectively 3 molecules, you will see that this is actually just a rotation around the carbon-carbon bond here. So, but it's mapped out, of course, as it should be as a local minima. However, if you then look at some higher energy transition or some higher energy structures, like let's say, for example, this one, where the system, that basically the chlorine atom is already dissociated, it tries to build out here or to form out a double bond, for example. There are more complicated examples here. They all correspond more or less to high energy structures here. And so this is, we're beginning to implement a proper visualization for this. So it is not yet perfect, but it should give you some idea of how the whole reaction network is mapped out. And if you have a reasonably well described system, so using, let's say, a proper force field for this, you should then be able also to see how the entire reaction network looks like, and then also basically the combination of reaction paths which exhibit the minimum reaction barrier that should be your reaction mechanism if everything goes right. And so with that, I think we are more or less out of time, I would say. So I would have some more exercises prepared for this. But given that we are a bit overdue, let me just point you to them. So there is something analogous, pretty much using with the only difference that it uses the basing hopping method. So it uses the same zinc oxide surface we just looked at. And it's indeed looks at different intermediate states for this water splitting reaction again. And another one is the example of these cobalt clusters here, where one basically studies the formation of these cobalt clusters by looking at where are potential adsorption sites for additional add atoms in their case. So, with that, are there any questions? So, I guess not. I would like you to, thanks for your, okay. Indeed, I would invite you to follow along or to, go through these exercises after. In the quasi-Newton method, you only, well, it is advisable to specify the coordinates because it tells your system where to go, right? So in principle, for very simple systems, you do not even need to do that. The system is able to figure out the lowest frequency mode by itself. However, if you have more atoms, if the modes become more and more complicated, involving more and more atoms, the distinction may be less clear. So it is advisable to tell the system how do you get an open shell coordinates? Open shell coordinates. I'm not sure how to. Can you quote the error maybe? So you can also, let's say the structure provided, the initial one, is close enough to the transition state. In your case, it will work. It should work without. But I would be indeed happy to help you out with an error if there is one. Because open shell error is doesn't make sense regarding coordinates. So you should have enabled. I think I know what you're seeing. What you may be seeing is if you haven't given it a spin of 1 here, so spin polarization of 1. If you didn't do that, so that would be my guess, if you didn't do that, it may complain about some closed shell solution with an odd number of electrons. Yeah. Okay, yeah, always welcome.
Is there any other questions?
Yeah, indeed, there will be Fedor answering questions as far as I know. And yeah, if you experience any problems or so, or technical issues for that matter. So we have plenty of material on the website, which should get you going for simple things. If you then encounter technical errors or so, yeah, there's also a ticketing system, support system if you encounter technical problems of any kind. So yeah, shall we conclude the session with that?